Okay, great. Can people online hear me fine? Well, I will assume so.
Yes, we can hear you.
Yeah,
Welcome, everybody. Welcome to today's CGD seminar. Before we dive into the exciting talk by Michael, I just want to make an announcement about the CGD Strategy and Engagement Day, which will happen on Thursday, the entire Thursday at Center Green. And we do want to encourage everybody who will be able to attend either online or in person to sign up for the CGD Strategy and Engagement Day event through your Google Calendar invite, so that like the organizers, they can get a very good head count of the number of people, and then later you will be like subgrouped into breakout groups. So yeah, please sign up, and then also let Elizabeth know that you will be attending virtually. Yes. So that will be the announcement. And today I'd like to introduce our CGD seminar speaker, Michael Diamond, who is an assistant professor in the Department of Earth, Ocean, and Atmospheric Science at Florida State University. His research mainly focuses on how the interactions between clouds and pollution particles affect climate, which is a very exciting topic. And he received his PhD in atmospheric sciences from the University of Washington, and then was a serious visiting postdoc fellow at the NOAA Chemical Sciences Lab and at CU Boulder before joining the faculty of Florida State University. Without further ado, I will just hand it over to you, Michael.
Great. Thanks so much for the introduction and for inviting me to talk today. I'm really excited to talk to you all about our new work showing the detection of large-scale cloud microphysical changes within a major shipping corridor due to the 2020 International Maritime Organization Marine Fuel Sulfur Regulations, which is a mouthful. So we'll go through what exactly I'm talking about with all of that. And we'll start with these regulations. Okay, so in 2020, the International Maritime Organization, which regulates global shipping, put a new limit on the amount of sulfur that you're allowed to burn in marine fuel oils. So traditionally, ships have burned the bottom of the barrel dregs, dirtiest fuel available, the stuff that you really don't want to burn on land near all the people, really. So the blue line here is showing the limit on open seas and how much sulfur you could have in that fuel, which was about 4.5% sulfur by mass before 2012, dropped to 3.5% by mass between 2012 and 2020. And then in 2020 did a huge 7-fold decrease in the amount you're allowed to burn, all the way down to 0.5% by mass. In the dark blue line here, these are values within these emission control areas. So you've already had some stricter regulations in place for the coastal areas of the US and Europe, but for most of the world and for the open oceans, the blue line here is kind of what we're looking at. So first of all, why did the IMO decide to ratchet up these regulations so strictly? And the answer for that really is about the air quality benefits of this regulation, particularly for coastal regions. Estimates shift a little bit study by study, but this is one estimate on the map here of avoided premature deaths due to this 0.5% sulfur cap from the previous 3.5% by mass cap, where you can see really big improvements in air quality and public health, especially in coastal regions of Eastern and Southern Asia. This regulation could be a really big deal. So that's a great news story here. But it does come with a potential catch. And in some of the recent news media articles about this, they've kind of been framing it as an unexpected trade-off. And that's maybe not exactly right? Even this perspective piece here in ES&T was written back in 2009. So we've known for a while that we might have this warming trade-off from these air quality benefits. And that's because these ships, they do emit CO2, shown from a simple climate model, the warming effect from an impulse of CO2 from the ships, and this red line here, that long-lived warming. But the sulfur from these ships also produces a short-lived but very strong cooling effect from that sulfur. And that we expect would be going away with these air quality benefits. So what is causing that? And that turns out to be how these ships and their pollution affect clouds. And kind of the famous example of this are the ship tracks that you can see beautifully in satellite imagery. So the sidebar I've had over here for a couple of panels now, each of these lines you can see in this MODIS imagery. If you knew where the ships were, you can go and trace that back to the individual ships and the pollution from its smokestack. And we've had evidence of this from the satellite record for a surprisingly long time. So the image I have here is the first instance of this in the scientific literature from the mid-1960s, already picking these out. This initial paper was written by an Air Force guy, so we got some cool hypotheses like, oh, maybe these could be missile trails or ship smoke screens, before settling on the more banal reality that this is just a pollution effect on the clouds. These ship tracks have been really helpful for testing hypotheses about some effects we'll learn about later, called the Toomey effect and cloud adjustments to the Toomey effect, which describes how these aerosol particles, these small solid and liquid particles in the atmosphere, affect clouds. But their overall climate significance has been really uncertain until recently. Most of this talk, I'll talk about some recent work that I think is going to help us nail this down a little bit more. But before we get to that, why do we have these cooling effects in the first place? And why are we focused on these marine clouds? And specifically, we're focused on these marine low clouds. But when it comes to Earth's energy budget, we're really going to care about two big effects from these clouds. One is their cooling effect, and that's just from reflecting sunlight. So you have these really reflective clouds over this almost black ocean surface here as seen from space. And that produces a strong cooling, shown by the blue colors in this plot up here. We also have warming via the greenhouse effect, normally thought of for CO2 and methane, et cetera, but clouds, especially clouds high in the atmosphere, have a substantial greenhouse warming effect as well. So we have a strong cooling, a strong warming. If we put those together, it turns out that on net, clouds cool the climate. They cool the climate overall, globally averaged, by an effect of about 20 watts per meter squared. Just a useful kind of benchmark to have in your mind when we're thinking about these watts per meter squared units is that a doubling of CO2 in the atmosphere, just instantaneously increasing the CO2 in the atmosphere and just letting everything else adjust to that, is about 4 watts per meter squared. So the net cloud effect is a cooling that's 5 times as strong as the warming from CO2. And of course, we don't expect to like totally lose all the clouds or anything like that, but it just goes to show that anything that's affecting these clouds can have a pretty strong lever on the global climate. And when we're looking at what really contributes to this net cloud radiative effect, a lot of it is these low altitude clouds near the ocean's surface, which is shown on the last plot here. And they're almost the entirety of this net radiative effect. So that's why we really want to focus on these clouds as being quite important. And as we'll see, some of the hotspots for these clouds in the North Atlantic here, North Pacific, this is also where we have a lot of ship traffic. So how does the pollution play a role in here? Why is the pollution affecting these clouds' radiative effects? And here I'm going to focus on these aerosol cloud interactions, or ACI, focusing on these shallow clouds over the oceans. So as I mentioned before, the first one of these effects we're going to call the Toomey effect, or the first indirect effect. To understand this effect, imagine that you're out over the remote ocean and you're given some amount of liquid water with which you can build a cloud. It turns out in Earth's atmosphere, all cloud particles need to form on a cloud seed in the atmosphere, an aerosol particle that can serve as a cloud condensation nucleus, or CCN. out over the remote ocean, there aren't that many of these around. We might have some wind kicking up some sea salt and maybe some other organics from the ocean surface, and that's really all we have to work with. So with that relatively small number of particles, we can build a cloud with a relatively small number of large droplets. Now imagine, let's have that ship come through. It's going to be spewing out these pollution particles from its smokestack. Now, for the same amount of liquid water, what we could do is we could spread that water out to a larger number of smaller particles. That is going to be a much more efficient way of spreading out the surface area of these particles for that same volume of water. And that's going to make that cloud brighter, so more reflective, and produce a cooling effect. And that is the Toomey effect. As you can imagine, the holding the liquid water that we have to work with constant is doing a lot of work in that hypothetical. So even though we have this Toomey effect, we can also have what we call adjustments to the Toomey effect based on what the cloud is doing that might either enhance or offset this cooling. So on the enhancing side, we could have drizzle suppression. So in that natural state where you have a small number of relatively large droplets, those droplets are going to be relatively efficient at colliding with each other and growing to sizes where they can produce these precipitation drops that are going to fall out due to gravity, so produce drizzle and some rain. We now have that ship go through. You have a bunch of these little cloud droplets. These are really inefficient at producing those precipitation-sized particles. So you can now imagine this cloud is going to potentially be thicker or last in the atmosphere for a longer time because it's not losing its liquid water to that drizzle process. So that's going to be an additional cooling effect on top of the Toomey effect. We could also have essentially the opposite effect happen in a cloud that maybe isn't so strongly drizzling in the base case. It turns out that having a bunch of these very small droplets, especially near the cloud top, increases the evaporation. Those small droplets are easier to evaporate, and that's going to drive more turbulent entrainment of the warm and dry air that's above this cloudy layer down into the relatively cool and moist cloudy layer itself and start evaporating that cloud away. And that's going to be a warming effect that could potentially offset and even counteract the Toomey effect. So when we put that all together, what we get is really large uncertainty in the magnitude of these aerosol cloud interactions. And here I'm showing kind of the famous image from the IPCC, where these warm colored bars are the warming effects due primarily to greenhouse gas emissions in the atmosphere. These cool colored bars are offsetting cooling effects. And what we can see is that the aerosol cloud interaction effect is the largest cooling offset to the warming. It actually offsets about a third of the warming we could have experienced due to anthropogenic greenhouse gas emissions up to the present day. What I really want you to focus on here is the size of these error bars. The magnitude of this effect for aerosol cloud interactions is really uncertain, and that uncertainty actually dominates the total anthropogenic uncertainty. So why is that? I just talked about these ship tracks that are these amazing natural experiments for aerosol cloud interactions. Why don't we have this locked down? And it turns out that even for these ship tracks, this paradigmatic example of aerosol cloud interactions in action, we still have a lot of questions about how these scale up globally. So it turns out that when you actually try to get an observational estimate, at least in the recent past, of these ship tracks, you wind up with a little bit of a paradox where you have all these tracks, but maybe they're not leaving so much of a trace on the global climate. So the image I'm showing here is from 1 year of manual detection. So just looking at these images in the satellite and actually picking out all of these little lines and building that up to show how much more reflection there is because of those ship tracks. And when they did that, laboriously, painstakingly integrated all of these individual tracks up, they got a global forcing of a fraction of a milliwatt per meter squared from these ship tracks. Again, that little benchmark in the back of your mind where a doubling of CO2 is about 4 watts per meter squared. The values over here are on the order of 1 watt per meter squared. This is negligible, tiny. But maybe we're just not so good at actually picking those out. Maybe we see them in the perfect conditions, but that's just the tip of the iceberg, and we're missing a lot of the tracks. So what if we tried to look at shipping corridors as a whole. And that's what Peters and colleagues did a couple of years ago, looking at these 3 shipping corridors here, identified. The different colors here are these shipping routes shown via their sulfur emissions. And what they did was a clever technique. They were looking at air that flows perpendicular to these shipping corridors under the assumption that as that air is approaching the shipping corridor, it's in a relatively clean environment, not as polluted because there aren't as many pollution sources over the ocean. Then once it hits that shipping lane, you have ships going back and forth, spewing out their pollution that should be blown with the wind as well. And then you have a polluted environment downstream. And hopefully we'd be able to see some kind of jump in the cloud properties, where if we're taking the Toomey effect right now, we would expect is an increase in the cloud droplet number and a decrease in the size of the cloud droplets that form as you go over that shipping corridor. And they do that on a couple years of satellite data, and they really weren't able to find anything. So the 0 line here is when it hits the shipping corridor, and you don't really see much of a change after the corridor, or at least not much of a change that isn't just the general trend that things were going in anyway. And that's surprising. And they later redid these results in a climate model and showed that the system here is just so variable. There's so much natural variability in cloud properties that even in the climate model where you kind of know the answer, you still can't get a signal out because of all of that very natural variation in cloud properties. And so this is a little bit surprising, though, especially that prior result, because when you put ship emissions in climate models, you do get a sizable forcing. It's not just the case that shipping is maybe a curiosity that helps us test some of these hypotheses, but it doesn't really matter globally. From some of these climate model results, this is just showing one example using 3 different plausible inventories of shipping emissions. In this model, you get forcings that are a substantial fraction of the total ACI, something like between 10% and even up to 40% of the total anthropogenic aerosol cloud forcing coming from the shipping sector. So what's going on here? And there are 3 recent advances that I think are going to help us answer that question, in addition to this kind of new natural experiment with the IMO 2020 regulations. So the first advance I want to talk about is enhanced detection using machine learning techniques, where I'm showing an example of that from one of these papers, 2 different teams with independent results. So the first one here I'm showing is Tianli Yuan's results from a nice paper last year, and the bottom from the team led by Duncan Watson Paris. In both these databases, there are some interesting differences between them, but most importantly, they both find an over an order of magnitude greater density of ship tracks than was previously possible with these prior papers with manual identification. So using the one I showed there, but also other methods. So that's really exciting. And what's even more exciting is that we were able to, or these teams are able to use these to look at the effect of the 2020 regulations on track identification. And they find overall substantial decreases in the detection of these ship tracks from satellite imagery after the 2020 regulations went into effect. But even though they find these really clear changes in the number of ship tracks that are forming, the actual impact on cloud properties has been a little bit tougher to discern, at least from these methods. So here, and we can focus on the right side here, we have our non-emission control area, which is going to show a stronger effect from the recent regulations. We see what we expect here from the immediately preceding period in the red to the 2020 period here in the orange, where we have a decrease in cloud droplet number concentration. So that's exactly as we expect should happen. Oddly, though, we actually get a further decrease in the size of the particles that's forming instead of an increase in the size of the particles, which is what we would expect from that prior result. And we have seen no difference in the brightness of the clouds that are forming. And the authors here expect that might have something to do with the varying background meteorology. So we don't really have a clean sense here of exactly what has this regulation done to the cloud properties themselves, even though we know we're getting a big decrease in the detection of these tracks. So what about the other data set? And here I'm focusing in on the Southeast Atlantic that we're going to talk about in a lot more detail in a little bit, where you can just see this nice, in this kind of concentrated corridor here, this big decrease in ship track occurrence. In terms of the counts here, a little bit over 150 prior to 2020, and then this big drop to like maybe 75 since then. And what this team did was they looked at just regionally averaged satellite retrievals of the cloud droplet number concentration. And what you see is that there's this big historic trend over the last decade in some of these areas, but there's not much of a break that we can tell, obviously, at least from visual inspection. Here in the Northeast Pacific, here in the Southeast Atlantic, maybe you could make the case that there's something going on after 2020, but it's not that distinct from the previous trend. So a little bit of a question mark here as well. Unfortunately, I don't have much time to talk about it, but another recent advance that's really exciting and that's going to give us some good information here is actually locating some of these quote unquote invisible or undetected ship tracks by actually tracking air masses if you know where the ships are, where the ship emissions are in the case of this team's result. And it turns out these quote unquote invisible ship tracks occur all over the place and also have slightly different properties than just the visible tracking. So that's really important to keep in mind. So both of these methods using machine learning or tracking individual air masses are kind of bottom up. Let's try to get an estimate from counting up all the individual ship tracks or all the individual visible and invisible ship tracks that we get just from air mass tracking. We could also try doing a top-down constraint. And that's what I'm going to talk about for the rest of this seminar here, where we're going to create counterfactual cloud fields over one particular shipping corridor, actually in the Southeast Atlantic. And this might be a little bit surprising because a few slides ago, you can remember, like, Michael, you just showed us that didn't work. They tried doing the shipping corridor method. They couldn't get a signal out of it. And it turns out that maybe that instead of looking at winds that flow perpendicular to the corridor, we're instead going to look at this particular corridor that was excluded from that paper because the winds flow almost perfectly parallel to the corridor itself and keep that pollution relatively constrained within the shipping area, which also just happens to fall right in the middle of this major subtropical stratocumulus stack. So to look at this, what we have first is our kind of quote unquote factual situation. So what actually happened in the observations or in the case up here, reanalysis. And this figure is from a 2020 paper that myself and colleagues wrote laying out this method. So we have in the top our surface sulfate, where we can see a pretty obvious perturbation where we think that shipping corridor should be. That's from the MERA-2 reanalysis. In the middle here, we have cloud droplet number concentration from the Bennartson routes product, where we see what looks like a suspicious line co-located with that shipping corridor. We could see also a divot in the cloud effective radius of the cloud size. So what we're going to do is we're going to take the spatial relationship between pixels on either side of the shipping corridor that we expect not to be affected by shipping emissions, because in our emissions database here, relatively low emissions on either side of this corridor, very isolated kind of ship superhighway here. And we're going to use those unaffected pixels to create a counterfactual situation of what should these clouds have looked like without the corridor being there, so the shipping effects removed. And that's what we see in this middle column, this counterfactual no ship situation. And we can interpret the difference between what we actually see and this no shipping corridor counterfactual statistical estimate as the causal impact of the shipping corridor on cloud properties here. What we see is we have a really obvious and strong signal in sulfate mass, but really excitingly, especially in the stratocumulus deck area over here, this big low cloud deck, we see a statistically significant and sizable increase in the cloud droplet number concentration and decrease in the effective radius. So exactly what we should expect to see from our understanding of the Toomey effect. And for the first time, we were able to show this at a regional spatial scale and a climatological time scale. So that was super exciting. So now the question we're going to ask is, can we use this method to learn something more about the IMO 2020 regulations? And before I do that, I want to go into a little bit more detail of how I actually make this counterfactual. And the method we use for that is called universal kriging. It's a classic geostatistical method. It was actually created in South Africa in the early 1900s, or the first version of it was, to look at mining applications. So we're estimating some variable at spots where we don't know it, or in our case, we're actually just going to pretend that we don't know what the variable is, just mask that data out within the shipping corridor, using the nearby locations of that same variable. So in this case, it's going to be these nearby values of cloud droplet number concentration. We're going to interpolate over, pretend this shipping corridor affected area is gone, and interpret ND over that. The way we do that is we have a mean value that's estimated from a regression model that we're going to train with geographic. And by that, I just mean latitude, longitude, and some permutations of latitude and longitude, and also cloud controlling meteorological factors. So here we're going to look at 3 factors that we know have an effect on cloud properties: the sea surface temperature, the estimated inversion strength, so how strong is the temperature inversion that keeps that warm, dry air separated from the cool, moist air under the cloud, and also the wind speed. So I'm showing that for the 2002 to 2019, so pre-2020 climatology on the top here. And then we're going to compare values from the immediately preceding 3-year period versus the 3-year post-2020 period that we currently have access to. So latitude, longitude, and these meteorological factors are going to help us create our mean function. Then the big insight for this kriging method is that the error or noise around the mean is assumed to be spatially correlated as a function of the distance between locations. So this is essentially a really fancy way of saying that grid boxes close by to each other look more similar than grid boxes further away do. And we can formalize that with the semi-variogram, which you don't have to worry too much about the math, how this actually works. But essentially, these black dots here are binned values of basically how close or how different are values for grid boxes that are really nearby as opposed to boxes that are further away. We're going to put a parametric fit to these observations with one parameter that talks how quickly that spatial dependence decays with distance, and then where does it decay to. And that's going to give us that spatial error term for our statistical model. This example here is for cloud albedo, or technically cloudy sky albedo, so how bright those clouds are. And for some of the variables, we're going to do some statistical transformations in the method. All of the results I'll show will have them transformed back into their original form. But I just want to air all the dirty laundry on this slide of what's kind of going into this model. And then the last thing I want to mention is that we also did have some potentially weird 2020 effects. So we're going to also account for that here. This plot here is just total shipping traffic. Again, you can see the North Atlantic and Pacific stand out, but also our Southeast Atlantic shipping corridor here. But if we zoom in on the 2020 difference here, overall over the world, there was a small decrease in shipping, maybe not as big as you would expect from the pandemic, but particularly in this corridor here, there's a small decrease in the main corridor, but maybe an increase further west. So because of that, we're going to kind of expand the westward or definition of shipping affected clouds to try to not accidentally have our results be contaminated by anything having to do with pandemic related movements in shipping. Okay, so when we do that, here are the results. I'm going to show them first for the pre-2020 climatology, and then just to look at how much noise we can get in these kind of just 3-year periods as opposed to climatology. This is the 3-year pre-IMO 2020 period, where in the first column here, we have our actual observed values from, this is from the series SSF 1 degree satellite for the Terra morning overpass. I'll go later why I'm specifically choosing the Terra overpass for this paper. And this is taken in the austral spring, so September, October, November, which happens to be the month of greatest signal. So if there's any month in which we can see, or any season in which we can see a signal, it really should be this one. So we have our counterfactual generated via kriging, via that algorithm I just described. And we have our difference, which we're interpreting as the causal effect of the shipping corridor here. And again, as we expect from those prior results, we still see this big decrease in cloud droplet size due to the effect of the shipping pollution. And the p-value here is calculated by how many of these grid points are statistically significant compared to what we might get from chance, just from spatially correlated noise. In the 3-year period before the IMO regulations went into effect, it's noisier, but we get something that looks pretty much the same. We can still see kind of the shape of the shipping corridor and a sizable decrease. So that's good. Going to a 3-year period maybe doesn't completely obliterate our ability to see any signals here. And now in this bottom row, we're looking at the post-IMO 2020 period. So all of the years 2020 through 2022. And what we see right away is that the effect of shipping on these clouds has diminished greatly. We actually no longer see essentially any signal at all in the northern part of this cloud area over here. And in the southern part, we can still discern a substantial shipping effect, but its magnitude is much less. It's a much lower decrease, which means the particle sizes are larger than they were in prior years. So that's a pretty strong signal right there. If we look at the cloudy sky albedo now, it's a little bit noisier. It's not as clean as the cloud droplet size retrievals, but we still see in the climatology a pretty strong sense of this cloud brightening effect in the main corridor. We get a pretty good sense of that in a 3-year period. And in the post-2020 period, we see a lot of that go away. And also the field here looks a little bit noisier. It's the blobs there maybe look a little bit closer to spatially correlated noise as opposed to the actual corridor diagonal line that we would expect, but maybe a little bit harder to see here. So what we're going to do to look at this in a little bit more detail, a little bit more resolution, is we're going to look at the central or average over this whole corridor, but the central 3 shipping affected boxes. So kind of ignore these flanks and look at that for all possible 3-year periods to see how extreme is the divergence in these 2020 to 2022 values. So we're going to show that here for the austral spring, where in these gray PDFs right now, on the top, this is the relative change in particle size for the climatology. So again, about this 4 to 5% decrease in droplets, the size of droplets that are forming because of shipping in this region, and about a 2% increase in the cloud brightness because of this effect. In all of these colored lines, these are individual 3-year periods, starting in the dark red from 2002 to 2004, all the way to in blue that 2017 to 2019 period. And the spread among these values shows just kind of how much noise we get around this climatology just from random chance, random changes in meteorology. So we're going to ask ourselves, is the 2020 to 2022 curve that distinct from climatology as compared to what we can normally get from just looking at a 3-year period as opposed to the full almost 20-year period? And it turns out the answer is yes. So for the top plot here, we could see with this 2020 to 2022 value, they are distinguishable from 0. So we still have an effect of shipping, but we are well separated from the climatology. We're actually within the 95% confidence bounds of these PDFs, separated from any prior 3-year period. And although this curve is still statistically significant, it's significant at a weaker degree than any of these curves, although they're all quite good p-values. If we look at the cloud brightening effect itself, it's similar but a little bit noisier. The 2020 to 2022 effect is not as cleanly distinguished from all prior years, but it is very clearly the weakest cloud brightening year on record in a way that's pretty extreme compared to what we can get just by chance. It's also the only one of these curves that is not significantly different from zero at its 95% confidence interval. So this is pretty exciting. We've detected, at least in this one season, a sizable effect due to the implementation of these IMO 2020 regulations, which gets us into kind of one of these implications, which is geophysical monitoring of compliance with IMO 2020 limits. So the traditional way that these are monitored, at least based on this data reported to the International Maritime Organization, is from the IMO kind of contracts out these different companies to do testing. So they go around the world and they test marine fuels for what's actually on the market that you can buy and figure out the fuel sulfur content of those. So pre-2020, when they went on and did that and reported the results back to the IMO, we had pretty consistently about 2.5% sulfur by mass in marine fuels that were out on the free market, which interestingly enough, you'll note is actually already below the previous limit. So in 2020, we have this new stricter limit take place, and immediately we see a big jump down, closer to or a little under 1% by fuel if you just sample the fuel that's available for sale on the market. Another way of looking at this is in 2019, if you just went to the market, only 22% of the fuels on sale would have been compliant with the IMO 2020 regulations. Whereas now, post-2020, between 70 and 80% of the fuels you can buy on the market are compliant with that 0.5% sulfur cap. This likely underestimates compliance because another way to comply with the regulation is to install a scrubber that takes the sulfur out of the exhaust and discharges it in wastewater. And you're allowed to carry non-compliant and burn non-compliant fuel if you are scrubbing it. So hypothetically, at least, the rest of this delta is being taken up by ships with scrubbers. But this is great. And we probably can trust what these companies are telling us, but how do we know they're not cooking the books? And that's where we can get into this ability to monitor with these geophysical retrievals, which I think is really exciting. So we have one version of that, which is just the ship tracks. We can see that decrease in ship tracks and know immediately that there's something that has worked in the IMO 2020 regulations. And I'll show here kind of a way of getting that out from my method. So here we're looking at the regional mean effective radius. So similar to what Watson Paris and colleagues were doing, trying to look at the whole regional mean cloud properties and see if we can get a trend over time, some obvious jump with the shipping regulations. The black values here are what we actually observe from satellite. The blue values here are the counterfactual that I estimate from this universal Kriging method. So again, larger cloud droplet sizes for all these years, and then that effect is very diminished in the 2022 or 2020 to 2022 period. We can estimate what should we have seen in a scenario in which the IMO 2020 regulations were just completely ignored. It's COVID, all the inspectors were staying at home, and the ships just kind of went wild and burned whatever they wanted. So we're going to estimate that value as this no ship counterfactual. So what we think we should have, what we would have seen in the absence of ships versus the normal, so the climatological mean, or that pre-2020 climatological mean difference between the counterfactual and the factual situation. So this delta here. And if we do that, we get this value for non-compliance. We would expect that we would have actually observed this value of effective radius if the IMO regulations had not been implemented successfully. So one big thing to note here is that this already is larger than any previous observation. And that's just due to meteorology and natural variability. So one important thing here is that the effect of shipping here is of similar magnitude to the effect of natural variability. What we can do now is we can take the difference between this non-compliance hypothetical and what we actually observed in the atmosphere and get out the true effect of the IMO regulations, which regionally over the whole region is about an 0.1 micron increase in the cloud droplet size, much larger in the shipping corridor itself. But again, this is averaging over the whole region. If, however, we had just taken some kind of persistence forecast, so let's say it's going to be similar to the pre-existing values, and let's just take as a hypothetical, we're going to estimate in our persistence forecast that the non-compliance would have been, if ships hadn't been compliant with the IMO 2020 regulations, we would just see the 2017 to 2019 results again. If that's our estimate of non-compliance compared to the actual estimate, that's about and we actually observed this value here, which is what we think we would have observed due to non-compliance, you would wrongly think that the IMO regulation went into effect and produced this large 0.3 micron increase in cloud droplet radius. So you would have a false effect that's actually a lot larger than the real effect because of that. So that just goes to show that you really can't just look at a simple time series and get this out. You actually do need to use some kind of advanced statistical method, either kriging here or these machine learning ship track identifications to monitor this, because the effects are on the same magnitude as natural variability. The other thing we could do here is measure the radiative perturbation. So here we're going to look at the Toomey effect, which in the closed curves here, we're calculating, don't worry about exactly how this is calculated, but in terms of the effective radius estimate. And in the black curves, we're going to calculate this directly with the change in cloud brightness. And there's some offsets, but for our intents and purposes here, these agree fairly well. In the blue, we have the climatology before the IMO regulations. In the black, we have the new values post-2020 due to the regulations. And we can interpret the difference here as the warming effect from this decrease in cloud brightening due to the IMO 2020 regulations, shown here in these red curves. In the austral spring season of peak signal, we get about 2 watts per meter squared, so order watt per meter squared increase in warming over the shipping corridor because of these regulations. If we look at the annual mean, which I have plots for the exact same analysis as we did for the austral mean, which is a little bit smaller, although you still have good statistical significance because you beat down the noise a little bit by averaging over all the months. But here we have something more like in the annual mean, this is about half a watt per meter squared, up to a watt per meter squared. So a sizable regional forcing, and what's kind of exciting for these estimates is they're a pretty direct estimate from the radiation itself of this perturbation. And these values are in line with global model values, maybe not exactly, but they're singing kind of from the same songbook, as opposed to those prior estimates from ship tracks alone. Both the global climate models and my values here are orders of magnitude greater than the warming you would get from just counting up the ship tracks, at least in that manual method. So what are the implications here for global warming, particularly after this really hot summer? There's been a lot of people who are interested in, could this be having an effect? And the answer is yes, but not one we would just obviously see, at least in the global mean. This is a nice schematic analysis from Berkeley Earth, looking at recent contributions from increases in greenhouse gas emissions, the recent shift from La Nina conditions in the tropical Pacific to El Nino conditions, the solar cycle going from a minimum in the solar cycle to starting to go towards a maximum now. And what we see there is that those mostly explain the recent uptick in warming. And we maybe have some interesting added on top of that, and coincidentally similar magnitude, that stratospheric water vapor perturbation from the Hunga Tonga eruption and these IMO 2020 fuel sulfur reductions at the global mean, something that we care about and that could be important, but something that you probably wouldn't see over the noise of natural variability. So that's kind of where we are for the implications for global warming, although this will increase in time and potentially be up to 0.1 degrees Celsius by the end of, or by the middle of the century, which is not insubstantial if you're thinking about Paris Agreement goals of limiting warming to 1.5 or 2 degrees Celsius above pre-industrial when we're already at 1.2. The implications might be much greater for regional warming, however, especially in the North Atlantic and Pacific, where these ship emissions are really highly concentrated. And if we look at, this is the North Atlantic temperature anomalies for this past July, really through the roof in 2023. And it's quite plausible, I think at least, that some fraction of this anomaly maybe is already a signal from this reduction in shipping, although there's going to be a lot more work needed to tease that signal out. There are also implications here for solar climate interventions. So looking out at this effect with ship tracks that we've already done accidentally in brightening the clouds, there have been proposals for, can we do this purposefully and deliberately increase the albedo of marine clouds and reflect some sunlight away to take the edge off of global warming? It wouldn't reverse all of the effects of climate change and wouldn't reverse them perfectly, but there is some sense that maybe this could reverse, at least temporarily, some of the effects of global warming as we scale up decarbonization efforts and carbon dioxide removal. So the US government's taken over the last several years, increasingly serious steps towards investigating this. This figure here is from a big National Academies report out a couple of years ago. And this kind of natural experiment that we just ran with the IMO 2020 regulations, I think can be really important for understanding or the research into, is this deliberate marine cloud brightening technically feasible? Especially, we can start using these IMO regulations to look at, are these local cloud adjustments going to enhance the effect via suppressing precipitation, or are they going to counteract the effect via increased entrainment in cloud burn-off? They're also, I think, going to be quite interesting for thinking about where do we actually see perturbations? Where do we get these cloud regimes that have been perturbed by the shipping? That'll help us understand which of these clouds are actually susceptible. And also in terms of how would we detect these signals now from IMO 2020 might be a similar problem for how do we detect signals for a hypothetical deliberate deployment. But zeroing back in on these local cloud adjustments, one of the big next steps for my group in thinking about the IMO 2020 effect is, how are the cloud microphysics, so the total liquid water in the cloud, going to change? And the reason I chose Terra for this first initial preliminary analysis of the effects is that from prior work, what I saw is that the effect in cloud brightening here in black is pretty much entirely driven by the decrease in cloud droplet size, shown by the blue curve here, versus the red curve here is hypothetical changes in liquid water in the clouds. And at least in this morning overpass, that was indistinguishable from zero in the morning. So I think pretty much in the morning, the Toomey effect is the whole story. That changes in the afternoon, though. When we look at the afternoon overpass of the MODIS satellite, what we see is that brightening due to the Toomey effect is almost completely offset by a decrease in the cloud water. So what we're interpreting as the entrainment effect of these clouds turbulently entraining more dry air and burning themselves out in the afternoon. So we really want to understand, with the new regulations in place, how has that affected these cloud adjustments, and how can we generalize that to other problems of overall aerosol cloud interaction due to industrial pollution, and to the specific case of potential deliberate marine cloud brightening. The other thing we want to do is actually compare these exciting new results. So I mentioned that my results are about an order of magnitude greater forcing than you get from just counting up manually detected ship tracks. But how does it compare to these automatically detected machine learning methods of ship tracks? And do we kind of converge at the same value, or are there still a lot of these ship tracks that remain quote unquote invisible to the ship track detection as well? And that is work that we have officially started actually just this month. So stay tuned for that. With that, I'm going to leave you with just some key takeaways, and then I'm excited to take your questions. So the key takeaways here, we were able to detect cloud microphysical changes after implementation of the IMO 2020 regulations. We were already able to detect before changes in chip track occurrence, but this work gets us one step further to the cloud properties and brightness themselves. We have strong evidence for that decrease in cloud brightness, although it's not quite as statistically significant as the microphysical changes. And we estimated a warming effect of order 1 watt per meter squared in the shipping corridor, which supports these climate model estimates of about 0.1 order of magnitude watt per meter squared itself. It's not precise enough to say it's exactly 0.1, but that's the right order of magnitude. And this is independent evidence, geophysical evidence for compliance with the IMO 2020 sulfur limits. So with that, I am excited to take your questions. Thanks so much for listening.
All right, thank you so much, Michael. This is a really exciting talk because you connect a lot of different aspects like the policy, regulation, science, and also statistics, and like a future like potential ways to to combat like global warming. So very exciting talk. Now I'd like to open up the floor to questions from the audience. You can actually post your questions on the Slido channel. And I will try my best. Okay. Let me see. Well, so we actually get a question from Dan. Nice talk, Michael. Do you have any thoughts on computing counterfactuals? For example, for computing additionality in geoengineering, when there is not a very clear space-time separation from natural variability. Should geoengineering experiments be designed to have accurate counterfactuals?
Yeah, that's a really good question. So I'll take the first non-geoengineering part of it first. So it's really hard. I've been wanting to, and like reviewers have kept on asking me like, oh, can we do the North Atlantic? Can we do the North Pacific? And part of the answer there is not super well because we don't have this nice, clean background condition. So part of what really lets us create this counterfactual is the fact that we have this situation here. We have really low emissions on either side of the shipping corridor. You have something not too dissimilar between Hawaii and California, but there it's like 3 diffuse corridors instead of 1 concentrated one. So I'm not super confident in being able to use that to actually get a signal out. So yeah, it is part of it is these really ideal conditions here. That does raise a question. So for marine cloud brightening, there have now been 2 kind of big reports of this from different parts of the US government, or I guess 3 actually, if you count the National Academy's report. There was also a workshop report that I should mention is not endorsed by the Departments of Commerce or Energy, just a panel of experts that they convened. But that one does specifically recommend, if you are serious about marine cloud brightening, you should do some outdoor perturbation experiments to understand it better. And we might want to do those anyway, just to understand aerosol cloud interactions better. But the first thing you would think of there is more on the scale of individual ship tracks. So kind of like in the image here. So maybe make a couple artificial ship tracks where we're really closely controlling the aerosol distributions and width, and study that and see if we can challenge our large eddy simulation cloud resolving models with can they accurately predict the adjustments there. And that would be a really big advancement in the science. If you then get to the next step, which some folks have started to think about, but we're kind of nowhere near this yet, of doing this more on to get a regional perturbation. I should mention, a huge gulf between the small scale outdoor experimentation and hypothetical future outdoor experimentation. Yeah, there is some like funky things we're thinking about of like, should we try to do something like the shipping corridor where we do a particular pattern that we think we might be able to get a signal out more strongly because of the winds, or try to spell out MCD over the South Pacific or something like that. Probably not those ones. We've had some fun thinking about it. But yeah, I think this does give us some ammunition for thinking about, are there clever ways we can design a field experiment that would help us with detection?
Mm-hmm. Yeah, thanks a lot for your reply. And we get another question from David. The question is, are there also potentially nighttime effects that wouldn't be captured by Terra or Aqua? And if so, do you have an idea of the sign and magnitude of those nighttime effects?
Yes. Yeah, and we could look at them a little bit in terms of cloud fraction, at least, which we can get from nighttime, although not as good a retrieval. But for the Terra morning here, I kind of said that we basically have the Toomey effect going on. This could quite plausibly due to be a diurnal compensation. So there is large eddy simulation evidence that in this cloud regime, what you can get from an aerosol perturbation is an enhancement of cloudiness overnight because you're suppressing precipitation. Drizzle in these clouds maximizes in the late even or late night, early morning time period. And then that entrainment effect, that kind of cloud burn off, is going to maximize in the early afternoon. You have kind of your maximum solar heating. And this morning might actually be what we're seeing is kind of zero effect because it's the transition between the enhanced cloudiness overnight to the decreased cloudiness in the afternoon. One thing I haven't done yet, but would really like to do is try to look at precipitation directly and see if we can get a precipitation signal, which I think would help us understand that. But my working hypothesis actually is that we are getting at least some of a cloudiness enhancement overnight that we're then losing throughout the day and is transitioning into a decrease over time. But I think the diurnal cycle is going to be important to resolve better here. I'll also mention we do have the Severi geostationary satellite over this region, and I have talked with some collaborators about trying to do this with or better resolve the diurnal cycle, at least during daylight hours also, with the microphysical signal using Severi.
Okay, all right. Thank you so much, Michael. I think the time is up, and also would like to thank all the great questions from our audience. Well, maybe you cannot see the audience, but I just want to give you a round of applause. And I'd like to remind you again, signing up for the CGD Strategy and Engagement Day, which is due by noon, right after the seminar. So please do that as soon as possible. Well, thank you so much, Michael, for coming here to give us a talk. And if you are interested or you have further questions, please send emails to Michael. Do you have your email up on your slide?
I should have put it up. Well, thanks so much for having me. And my email is msdiamond@fsu.edu.
Yes, because I know a lot of folks at the CGD, they're interested in this marine cloud brightening thing. So yeah, you can get in touch with Michael if you have further questions and if you want collaborations. Okay, all right. Thank you again for your attention, and I hope to see you next time. Bye-bye, Michael.
Thanks. Bye.
Bye.